whenever we have emission from a surface and there is another surface nearby, what is normally going to happen is that all the emission which is coming from surface 1 will not strike surface 2. Therefore, the energy emitted by surface 1 may not be intercepted by surface 2. How much of energy, what fraction of energy that is emitted by surface 1 which is going to fall directly on surface 2 is known as the view factor. So, if the two surfaces are very close together, then the view factor of 1 to 2 would be obviously equal to 1. That means all the energy emitted by surface 1 is going to incident on surface 2 directly. So, this concept of view factor, how much of the emitting surface is visible from another surface nearby, is important because it would give us a tool during our calculation of emission and interaction, radiative interaction between surfaces which will form part of an enclosure. So, whenever we would like to design an enclosure and we would like to find out how much and the three surfaces forming the, let us say the three surfaces forming the enclosure are at different temperatures. One is receiving the heat, the other is emitting the heat, and maybe the third surface is insulated. So, how much of interaction and how much of energy is going to incident on one surface is going to come out of the other surface, how much of energy is to be extracted from a third surface to keep it isothermal. All these are important in industrial calculations. For example, the design of a furnace. So, the concept of view factor is therefore extremely important in the designing of radiative heat exchange processes in an enclosure, for example, in a furnace. And we know what are the uses of furnace, from baking a surface at a specific temperature to exposing another surface at a very high temperature. The third application could be drying of a surface through radiative heat and so on. So, the examples of radiative heat exchanger in a furnace are many and from different fields. But the first thing that one needs to know is what is the fraction of energy emitted by one which is going to be intercepted by the second directly without considering reflection of energy from the adjoining surfaces. So, this is view factor which we have discussed in the previous class, and we have also seen some of the properties of view factors. For example, if you take a view factor and you find out the view factor of that surface to all these surfaces nearby, which forms an enclosure. So, whichever room that you are sitting right now, let us say the floor of that room is your surface 1, and then you have 5 more surfaces which are forming the enclosure, the 4 walls and the roof, which forms, so these 6 surfaces will form the enclosure. Now, when you consider the surface on the floor, then it has the possible view factors are F1, where 1 refers to the floor, F12 from the floor to the roof, F13, 14 and 15. These are all the walls which we have, and interestingly there is a view factor of the floor to itself. That means it is possible that some of the energy emitted by the floor is going to be absorbed by the floor directly. Now, when you consider the floor, obviously if the floor is plane and level, there is no chance of energy emitted by the floor absorbed by the floor itself. So, F11, which is the view factor of the floor to itself, 1, that would obviously be equal to 0, and the sum of all other view factors would be equal to 1. So, the first rule is the rule of summation rule, which tells you that the sum of all possible view factors from a surface would be equal to 1, which obviously is intuitively correct as well, since the view factor gives you the fraction. So, the sum of all fractions of energy coming from a surface has to be equal to 1. The second one which we have which we have derived in the last class is the concept of reciprocity, the reciprocity relation, where we have shown that A1 F12, A1 being the area of surface 1, F12 is the view factor of 1 with 2 should be equal to A2, that is the area of the second surface times F21. So, the reciprocity would give another set of relations between surfaces which are forming an enclosure. So, the first thing is summation, the second rule is the reciprocity relation, and the third rule, which applies to convex and plane surfaces, for which you can say that A11 is equal to 0. So, for a convex or a plane surface, no fraction of energy emitted by the surface is going to be absorbed by the same surface, which we cannot say for the case of concave, because when you think of a concave surface, part of the energy emitted by the surface will probably be absorbed by the surface itself. So, that is fine, but and we have also seen how one can analytically calculate the view factor of different surfaces, and the view factor of, obviously when you talk about the two surfaces, the view factor would depend on the magnitude of the area. That means, whatever be the length scale associated with area 1, whatever be the length scale associated with area 2, and obviously the distance between the two. So, the view factors are normally expressed graphically based on the relevant dimensions and the separation between the two surfaces. So, in your text and in any text, you would find that these view factors are calculated for some of the standard surfaces, and those standard relations for view factors, the results for the view factors are expressed in graphical form, and it would be very useful to use those graphs for a number of applications where at least you would be able to find one of the view factors. Now, if you find one of the view factors, then the next thing one should do is try to see if you can use summation rule, reciprocity rule, or the nature, whether it is curved or a flat surface rule, to see if other view factors which are forming the enclosure, if the other view factors can also be evaluated. So, we would see some of the problems towards the end of this class, but I will give you some idea of how the results of view factors for common surfaces are expressed in the graphical form. So, the first one that you would see over here, this is the view factor of an elemental area dA1 to a surface A2 with dimensions of L1 and L2, and D is the distance between them. So, dA1 is the elemental surface, D is the distance between the surface and the tip, this edge, the corner of the surface A2, which has dimensions of L1 and L2. So, you will see a number of curves like this, where the x axis is L2 by D, D is the separation, and the family of curves are for different values of L1 by D. So, this curve is elemental, this is f dA1 to A2 from an elemental surface to a rectangular surface which is having an area A2 and dimensions L1 and L2. So, the curve 1 is for an elemental surface area. Please note the location of the elemental surface with respect to the surface. So, that is the corner is directly above dA1. So, if you know the values of L2, D and L1, you should be able to find out what is the value of the view factor. Now, we come to this one. So, this is going to give you f A1 to A2 from a rectangular surface A1. So, this is the rectangular surface A1 to another rectangular surface A2. So, this top surface is A2 which are parallel to each other. Parallel and directly opposite. So, here you see that this is a cuboid and we are talking about the base area which is denoted by A1. The area which is parallel and directly opposite to A1 is obviously the top of the rectangle. So, I am trying to find out what is F A1 A2. So, this is from a rectangular surface A1 to another rectangular surface A2 which is parallel to A1 and directly above or directly opposite to it. So, these are also expressed in graphical form. The L1 and L2 are the dimensions of the rectangular surface, d is the distance between them. So, the x axis as before is L2 by d and the family of curves are for different values of L1 by d. So, one would be able to obtain what is going to be the view factor for such a case. And if you find out f A1 to A2, A1 to A3, A4, A5, A6 can simply be calculated using any of the known relations like reciprocity and or the summation rule. The third one, again it gives you the value of A1 to A2 from a rectangular surface A1. So, this is your A1 to a rectangular surface A2 which are touching each other. So, that means which are adjacent and perpendicular to each other. So, you can think of, you can imagine A1 and A2 are the two sides of this rectangle, or if you open a book like this, where they are perpendicular to each other, the two surfaces are perpendicular to each other, then the view factor of this surface to this surface which is adjacent, that means they are touching each other and which are perpendicular to each other. It is that view factor that we are trying to find out in here. So, inside a rectangle, the base and the adjoining surface is the value which we are trying to get. So, again it is going to depend on L1, L2, that means the length scales which define the area. So, if you look over here, then you have different value. So, this is L2 by W and this is L1 by W, where W is the width of these two plates. L1 and L2 are the other length scales which are present here. So, again you can find what is the view factor from here. The last one that you see is F A1 to A2 between two coaxial parallel discs. So, these two coaxial parallel discs, they are, so therefore, the center of this and the center of this one, they are coaxial, and you should be able to find out what is the view factor of one with respect to the other, provided you know what are the values of R1, R2, that means the radius of disc 1, radius of disc 2 and the separation between the two. So, the x axis is L by R1, the y axis, the different values of the curves are R2 by L, and you can find out what is F A1 to A2. So, using the mostly these are the four fundamental figures that can be used to find out what is the view factor of a surface to the other. In some cases, a combination of these would be required. In most of the cases, the view factor obtained from these graphs are to be combined with the summation rule or the reciprocity rule relation to obtain the unknown view factor, the other unknown view factors. In some cases, you really have to do some sort of an algebra in order to find out what is the view factor for such cases. So, we will quickly see some of the examples of the use of these charts to obtain the view factors of unknown surfaces. So, the first one that we are going to do is, let us think of a rectangular surface like this. So, this is the rectangular surface and you have, but this is a cube. So, all sides are same and you have to first find out what is the view factor from the base of a cube to each of these surfaces. Okay. So, we'll denote the base surface as 1, the top surface as 2 and the others are 3, 4, 5 and 6. So, from the figure, that is this figure, you are going to find out what is the view factor. Your L1 and L2 are the same here and it is also equal to D since it is a cube. So, your L1 by D is 1, L2 by D is 1. So, from the corresponding point where L2 by D is equal to 1, you go all the way to the curve which corresponds to L1 by D equals 1 and you reach the value of f A1 to A2. Once again, A1 is the base of the cube, A2 is the top of the cube. Since it is a cube, L1 is equal to A2 is equal to D. So, that means both these ratios would have value equal to 1. So, you go up to the right curve and find out what is f A1 to A2. So, that is the first use of this curve. So, from the figure, what you are going to see that you are going to check on your own is f12 is equal to 0.2. That is from the figure. You can also write that Fij is equal to 1 and in this case I varies from j varies from 1 to 6 and F11, that means the view factor of 1 to itself would obviously be equal to 0 since it is a flat surface. F12 we have just found out to be equal to 0.2 and by symmetry, since it is a cube, F13 would be equal to F14 would be equal to F15 and F16. Fij for j 2 to 6 should be equal to Fij would be equal to 0.2. So, F13, F14, F15 and F16 using the summation rule and knowing the value of F12 to be equal to 0 and knowing the symmetry involved in a cube, your Fij should be equal to 0.2. So, all from 1 all view factors except to itself would be equal to 0.2. So, F12 is 0.2, 13, 14, 15 and 16 all are going to be equal to 0.2. The second one is a cylinder like this and the question that you have to answer is from the what is the view factor. So, all these are what are the view factors. So, this is for 1 from this, and this is from the base of a cylinder of radius r and height L to its top surface. And the cylindrical surfaces for r equals L. So, we need to find out what is the view factor from the base of a cylinder of radius r. So, this is radius r and length L. So, from the base of this surface to the top of the surface for the case when r is equal to L. So, what you need to do is you need to use obviously this figure, but in this case r 1 would be equal to r 2 and the value of L is assumed to be, for the problem given, r 1 is equal to r 2 is equal to L. So, therefore, your L by r 1 and r 2 by L will have values equal to 1. So, you can read what is the value of f 1 2. So, if the radius r and L, if both are same, then from the graph, from figure, you would see that you should check it on your own. F 1 2. So, this is my surface 1, this is my surface 2, and the curved surface is 3. So, f 1 2 is 0.2, and then I invoke summation rule, which says f 1 1 is 0, f 1 2 is equal to 0.2, and therefore, sorry, this is 0.4, f 1 1. So, this is 0.4, and therefore, f 1 3 must be equal to 0.6. So, this is definitely the value that we are looking for. Since f 1 1 is 0, f 1 2 is equal to 0. When you use reciprocity relation, then A 3 f 3 1 should be equal to A 1 f 1 3. So, we need to find out what is the view factor of 3 from 3 to 1. So, f 3 1 is A 1 by A 3 f 1 3. We know what is the value of f 1, we know the value of what is f 1 3. So, your f 3 1 would be equal to A 1 by A 3 times f 1 3, and when you put the values in there, you are going to get equal to 0.3 for r equals L. So, the value of f 1 3 you have already obtained to be 0.6. So, A 1 by A 3 ratio for r equals L would give you the value of f 3 1 to be equal to 0.3. So, what you have obtained is f 1 2, f 1 3 and f 3 1. So, all values are obtained in this fashion. The third one is more interesting. So, the third one simply tells you that this is the between the surfaces of two concentric spheres with A1 and A2 being the inner and outer surface. So, this is A1 and this surface is A2. Okay. So, obviously, what we can see from here is that for constant F11, this is concentric spheres, and we have something in between the intervening space. F11 has to be equal to 0, because F11 constitutes a convex surface. So, for a convex surface, the view factor to itself of the surface to itself must be 0, because any emission coming out of A1 is not going to fall directly on A1 again. It may get reflected from the inner surface and may incident on surface 1 again, but the definition of view factor is that it is the emission, the fraction of emission which falls directly, which is emitted by a surface and falls directly on itself. So, since for a convex surface there is no chance of an emission being incident again on the same surface, therefore, F11, where 1 refers to the inside the surface area of the inside sphere, F11 must be equal to 0. And you can also say that the summation rule, and physically you can imagine that all emission emitted from 1, since it is inside the larger sphere, all emission from 1 must fall on 2. Therefore, the view factor F11 may be 0, but F12 will have a value equal to 1. So, what we can write from here is that the summation rule and common sense that will tell you that F12 will have a value equal to 1. So, this is summation rule. On the other hand, you can see that some of the energy which is emitted from 2 is going to strike 1, but some of the energy emitted from 2 may strike 2 itself once again. So, this since A2, the inside area of the outer sphere is a concave one, I cannot say that F22 is equal to 0. So, saying this would be incorrect, since it's an since this is that is not the case. So, the two view factors. So, this is for surface 1, and for surface 2 I need to find out what is F22 and what is F21. I cannot say F22 to be equal to 0, which is incorrect. So, rather I should concentrate on F21. Now, how can I find F21? I know what is the value of F12. So, if I know F12 and if I know F12, then F21 can be calculated from reciprocity relation. That is the other relation which we have. So, reciprocity gives us A1 F12 must be equal to A2 F21. That is the reciprocity relation. So, F21 is equal to A1 by A2, since F12 is equal to 1. So, that is the other relation, and you can then therefore calculate F22 from summation as F21 plus F22 is equal to 1. So, this must give you F22 as 1 minus A1 by A2. So, that is the other relation which I would like to highlight a little bit more. So, simple use of reciprocity and summation would give you the value of F22. Now, A1 is the surface area of the inner sphere and A2 is the surface area, inside surface area of the outer sphere. Now, let us think of a situation in which a very small sphere is placed inside a very large sphere. So, the sphere inside is very small, therefore, A1 is small and the sphere outside is very large and therefore, A2 is large. If that is the case, then all emission coming out from surface 2 is going to fall directly on itself. The small area, the small sphere which is located at the center, it really does not matter. So, common sense tells us that when A2 becomes very small, A1 becomes very small, the inside sphere becomes very small, we can, in the limiting case, we can assume that it is not going to absorb anything which is coming out of 2 and therefore, the fraction of energy emitted by 2 which is going to be incident on 2 itself directly will have to be equal to 1. So, whatever we thought to be correct from an intuitive point of view, if you look at the equation, this is going to corroborate that. So, when A1 becomes small and A2 becomes large, F22 will have a value equal to 1. So, what I would suggest is, if you look at your textbook and some of the other textbooks on radiative heat transfer, you would see that there are several configurations which are provided as examples or as exercises for you to practice to see whether or not you can correctly evaluate what is the view factor for such cases. So, I urge you to practice. The concept is very simple, the two relations are also very simple, the summation rule and the reciprocity relation. I have shown you 3 examples of how to calculate the unknown view factor. There are examples which you should solve yourself to see if you have understood the concept clearly. And as I mentioned before, the concept of view factor is going to be extremely important when we are going to calculate radiation exchange between surfaces which form an enclosure, for example, a furnace. So, we will see how this is to be done in the subsequent classes.